of some countries specify a value of 0035, which does not make an appreciable difference in the computed strength of a member. That's kind of important. 003 is not universally accepted. Some use 0035, but it doesn't make much of a difference in the computed value of flexural strength. This simply shows that the 003 that has been chosen by ACI 318 for adoption is a good lower bound value based on a lot of tests. In this portion, I have taken a lot of particularly pictures from this source, Notes on ACI 318-08, published by the Portland Cement Association. That publication now is discontinued, unfortunately, and Portland Cement Association has been reduced to a small fraction of what it used to be. So there is no hope that that publication we will see in the future anymore. But that was a very important publication in explaining ACI 318 to the design profession. Anyway, I have taken quite a bit of these figures and things from that source as noted here. Yeah. Design assumption number 5, the stress-strain relationship of concrete in compression. Those look as you see in the picture. Okay, it on the y-axis is stress, on the x-axis is strain, and from one curve to the other, we are looking at higher and higher strength concrete, 1,000, 2,000, up to 6,000 psi. These are tests that Surusha and his students did at Northwestern University ages ago. Anyway, this is very typical of concrete stress-strain relationship. The relationship between concrete compressive stress distribution and concrete strain shall be assumed to be, so actual stress-strain relationship is as you saw in the picture. However, the relationship between concrete compressive stress distribution and concrete strain shall be assumed to be rectangular, trapezoidal, parabolic, or any other shape that results in prediction of strength in substantial agreement with results of comprehensive tests. This is all very important, but probably not understandable in upon reading. So let us look at this. So strain distribution is linear. The portion of the beam or section above the neutral axis is in compression. These are the compressive strains. For each strain, there is a corresponding stress. And if the stress-strain curve looks as I showed you, the corresponding stress distribution will look like this. Are you with me? Okay. So this zero axis is now the neutral axis. And as the strains increase, the stress increases up to the peak, and then it begins dropping. So the actual stress distribution is as shown in the picture. F sub C prime is the specified compressive strength, and this is established by testing cylinders. And anyway, F sub C prime is a defined quantity, okay? Specified compressive strength. Now we are postulating that this maximum stress is K3 times F sub C prime, and this K3 can be equal to 1 or a little bit different from 1. Okay, the peak stress can be F sub C prime or a little bit more or less depending upon a lot of situations. The resultant compressive force is at a distance of K sub 2 times the neutral axis depth from the extreme compression fiber. That's what we are saying. We are also saying that this total compression in the concrete is the K3 F sub C prime times the width of the section B times the neutral axis depth C if K3 F sub C prime were the uniform stress over the compression zone, then the total compression would have been K3 F sub C prime times the width of the section B times the neutral axis depth C. But K3 F sub C prime is not uniform over the compressive zone. What is uniform, or we can think that this can be translated into a uniform stress distribution over the compression zone, where the uniform stress is a K1 times this K3 F sub C prime. Okay, so the peak value of the stress is K3 F sub C prime. That multiplied by a number smaller than 1 would be the equivalent uniform stress across the compression zone. Concrete compressive stress distribution can be determined by defining the 3 parameters K sub 1, K sub 2, K sub 3. Now, equivalent rectangular stress block. So stress-strain distribution is nonlinear. If you follow the nonlinear stress-strain distribution, this is your compression block in the concrete. And to do anything with this, we need to determine K sub 1, K sub 2, K sub 3. Okay. Now, ACI tells us that this actual stress distribution for calculation purposes can be replaced by this equivalent rectangular stress distribution. This is extremely important. Okay. In this rectangular stress distribution, the uniform stress is 85% of F sub C prime, 85% of the specified compressive strength. The depth of the stress block, lowercase a, is the neutral axis depth multiplied by a factor beta sub 1, whatever it might be, is smaller than 1. Okay. And because it is a rectangular distribution, the resultant compression is at a distance of 1/2 of the stress block depth from the extreme compression fiber. So this distance is A over 2. The total compression is 85% of F sub C prime times the width of the section, which is into the screen, times the stress block depth A. Okay. So equivalent rectangular concrete stress block. The requirements that we consider this kind of a nonlinear stress distribution in the concrete are satisfied by an equivalent rectangular concrete stress distribution. Okay. I'll elaborate a little bit more. Okay. So the beta sub 1, remember the stress block depth is the neutral axis depth multiplied by beta sub 1. Beta sub 1 is 0.85 up to a concrete strength of 4,000 psi. It drops to 0.65 at a strength of 8,000 psi, and beyond that it remains level at 0.65. So 0.85 up to 28 MPa, 0.65 beyond 56 MPa, in between 28 and 56, we do a straight line interpolation between 0.85 and 0.65. Okay, now remember, we have two basic the conditions we are dealing with: force and moment equilibrium and strain compatibility. In our case, strain compatibility simply means straight line strain distribution. Okay, going back to force equilibrium, this is the total compressive force, 85% F sub C prime times, this is the uniform stress across the stress block, the stress block depth A, and the width of the section B. That has to equal the total tensile force, which is the total area of tension reinforcement multiplied by the yield strength of the tension reinforcement, assuming obviously that the tension reinforcement is yielding, that the strain in the tension reinforcement exceeds the yield strength, that the yield strength. So if we equate the compression with the tension based on force equilibrium, the neutral axis depth comes out to what you see here. Okay, and then from moment equilibrium, the nominal moment strength, the moment that, okay, let's look at what we are doing. We are taking either the compression of the tension force and multiplying that by d minus a by 2. So let us say we take the tensile force, A sub S F sub Y. That is a tensile force and a compressive force. The distance between the two is D, the so-called effective depth, is from the extreme compression fiber to the tension reinforcement, to the centroid of the tension reinforcement. The distance between the compression force and the tension force is D minus A by 2. So the moment is either the tension force or the compression force multiplied by this distance of D minus A by 2. Now this moment is the nominal moment strength, because we have postulated that the strain at the extreme compression fiber of concrete is 003. So we have an expression for the stress block depth and also the nominal moment strength, as we call it. Remember the terminology from yesterday. Okay, so nominal flexural strengths computed using the rectangular stress block are in substantial agreement with the results of comprehensive tests. I would like to go back to the language that I said was not understandable upon reading, but this is important language. ACI 318 is not telling you to use the rectangular stress block. It never has told you so. It simply says the relationship between concrete compressive stress distribution and concrete strain shall be assumed to be, you can assume it to be rectangular, trapezoidal, parabolic, or any other shape. You can postulate it to be anything you want. However, what you postulate must result in prediction of strength in substantial agreement with results of comprehensive tests. So we are now saying that we have postulated, or ACI 318 has postulated, a rectangular stress distribution, but that would be valid only if the results are in the results of computation are in substantial agreement with the results of comprehensive tests. Okay, so that's the topic we are on now. Flexural strengths computed using the rectangular stress block are in substantial agreement with the results of comprehensive tests as long as the tension reinforcement yields. And there is really ample evidence of that, as shown in this picture. This is nominal strength calculated using the rectangular stress block. This is tension reinforcement ratio multiplied by yield strength of the reinforcement divided by the specified compressive strength. The dots are experimental values, and the line is the nominal moment strength calculated using the ACI rectangular stress block. So you should have no qualms about using the rectangular stress block. Okay. Now I do want to make a point which I think is important. So you can assume anything provided it will give you strength in substantial agreement with test results. Okay. Way long time ago, I had a friend, Muharram Sargin. He decided, and he published this. I forget now, it was so long ago, I won't be able to find it. But he took a stress, so this is the strain distribution. He took a stress distribution, which was the reverse, highest at the neutral axis, going down to zero at the extreme compression fiber. It was obviously an absurd stress distribution. And he showed that even that absurd stress distribution gave him nominal strength in substantial agreement with test results. And that is because of something I said yesterday you may or may not have caught on. As long as it is an under-reinforced beam, the behavior is determined almost entirely by the reinforcement properties. The concrete plays a very modest role, if any. So what you postulate to be the stress-strain relationship of concrete does not really matter. It begins to matter as the section has more and more reinforcement, or as you change from a flexural section, a beam section, to a column section. You put more and more axial load on the section. Now the compression properties of the concrete become important. So remember these basic things, that as long as it is a beam, what the concrete does is relatively immaterial. It's the reinforcement that counts. Okay, now a little bit of repeat from yesterday, which I will do very, very quickly, but this is part and parcel of what we need to discuss today. Compression control sections, remember, we defined the net tensile strain. Net tensile strain, once again, is the strain in the extreme tension reinforcement corresponding to a strain of 003 in the extreme compression fiber of the concrete. If the net tensile strain is 002 or below for grade 420 reinforcement, then your section is compression controlled, 002 or less. If the net tensile strain is 005 or more, your section is tension controlled. In between, if the net tensile strain is between 002 and 005, your section is a transition section. I showed you this picture yesterday. This is a repeat, and what I'm saying is also a repeat because it is that important. So if the net tensile strain, which is the strain in the reinforcement corresponding to 003 in the extreme compression fiber of concrete, if that is less than or equal to 002, you have a compression control section. If it is larger than or equal to 005, it's a tension control section. In between, transition section.
No.
Okay, we looked at the phi factors also yesterday. So if it is a tension control section, the phi factor is 0.9. If it's a compression control section, spirally reinforced 0.75, tight reinforcement 0.65, and between 002 and 005.
Dr. Ghosh, just wait, just wait. Yes, Dr. Ghosh, you can continue.
Okay, yeah. Between 002 and 005 epsilon sub t values, we interpolate phi between either 0.65 or 0.75 and 0.9. We went over all of this yesterday. Okay, so we talked about nominal strength calculation. Design strength would be phi times the nominal strength, and the phi is going to be 0.9 for tension control sections, or a little bit less than 0.9 for transition sections. Okay. Remember, we can have transition flexural sections because epsilon sub t cannot be any less than 004, but it can be less than 005. This is what we established yesterday. Okay, a simple example, and in this segment I have included a number of examples to drive the points home. So this is a rectangular beam section, 300 millimeters, 500. Now I have used metric units, but I have told you on previous occasions that means that I don't have any feel for the numbers. So that is just a matter of fact. So without translating, I don't know what 500 millimeter means, but it's probably better this way. So 300 by 500 millimeter section, 3 25 millimeter bars as tension reinforcement. The clear cover is 40 millimeters. That's an inch and a half. F sub C prime is 40 MPa. That's pretty good strength. 40 is almost 6,000. 5,500, something like that. F sub Y is the grade 60, as we call it, 420 MPa. Okay, so the section is given, the material strengths are given. We will calculate the flexural strength of this section. It's a singly reinforced beam section, meaning there is no compression reinforcement, only tension reinforcement. Okay, so this is the same picture as before, nothing to add. The section, the strain distribution, the stress distribution is a rectangular stress block as described earlier. Okay, so first is effective depth. We have a total depth of 500 millimeters, 40 millimeters of clear cover, 12 millimeters is the diameter of the stirrup that has to be around the longitudinal reinforcement, and the longitudinal reinforcement is 25 millimeter diameter. We go to the center of the longitudinal reinforcement, so half the diameter. Okay, so 500 minus clear cover of 40 millimeters. Not shown in the picture is there is a stirrup or a tie or something around the bars. We need them even for construction reasons. So that is 12 millimeter diameter. And then we take away half the diameter of this bar, the 25 millimeter diameter bar. So that gives us an effective depth of 435 millimeters. The width of the beam is 300, and the three number 25 bars have a total cross-sectional area of 1470 square millimeters. Assuming that the tension reinforcement yields, this is our force equilibrium equation. This is the concrete compression force. This is the tension steel force. There is nothing else. There is no compression reinforcement or anything like that. So we are just saying compression force is equal to tension force. That will give us the stress block depth as equal to that, and that comes out to 60.5 millimeters stress block depth. The neutral axis depth is stress block depth divided by beta sub 1. Remember, the stress block depth is beta sub 1 times C, the neutral axis depth. Beta sub 1 varies between 0.85 up to 28 MPa, and after 56 MPa, it levels up at 0.65. We are at 40 MPa, which is between 28 and 56. So by linear interpolation, beta sub 1 comes out to 0.76. So neutral axis depth for a 60.5 millimeter stress block depth comes out to 79.6 millimeters. Oh, sorry, prematurely. At nominal strength, strain in extreme compression fiber is assumed to be 003. So from a linear strain distribution, which we are postulating, the tensile strain in the reinforcement comes out to 0.013, which is larger than epsilon sub y. Okay, so all we are doing is, if it is 003 here, what is the strain at the location of the centroid of the reinforcement? And that came out to 0.013, verifying that the tension reinforcement actually yields as we assumed in the first place. So now we have everything we need for the calculation of nominal moment strength. It is the tension force of the compression force, both are equal, multiplied by the distance between the two, the lever arm, which is the effective depth minus 1/2 of the stress block depth. So A sub S is 1470 square millimeters, F sub Y is 420 MPa, D is 435 millimeters, A we calculated 60.5 millimeters divided by 2, and all of that gives us 250 kilonewton meters of nominal moment strength. Okay. Pretty easy calculation. And since this is now also our net tensile strain, the strain in the reinforcement corresponding to a strain of 003 in the extreme compression fiber is also net tensile strain. That exceeding 005 means the section is tension controlled, so the phi factor is 0.9, and that means the design strength is 0.9 times the 250 kilonewton meters of nominal strength that we calculated, and that comes out to 225 kilonewton meters. Okay, so that's pretty simple. Now we will go to a doubly reinforced section. We have tension reinforcement, we have compression reinforcement, A sub S, A sub S prime. The strain distribution is the same, except that at the centroid of the compression reinforcement, we are saying that the strain is epsilon sub S prime. So in the tension reinforcement, it's epsilon sub S. In the compression reinforcement, it is epsilon sub S prime. The rectangular stress block is the same as before. This is the compression concrete force. This is the tensile steel force. Additionally, we now have a compressive steel force, which should be A sub S prime, the total area of the compression reinforcement, multiplied by the stress in the compression reinforcement, F sub S prime. That has to be determined. Okay, so I think everything is clear cut. I'm still taking quite a bit of time because I want everything to be understood. And if not understood, jot down your question and we'll come to those at the end. Okay. So the nominal moment strength from moment equilibrium now is the so 0.85 F sub C prime is the uniform compression across the stress block times the lever arm between the compression and the tension force D minus A by 2, and the compressive steel force is A sub S prime F sub S prime, and the lever arm between the lever arm between this and that is this distance should be marked. This distance is D prime. I think it was probably in the previous picture. Anyway, take it from me. I don't see the D prime marked here. So this distance is D prime. So the distance from the compression concrete force to the compression steel force to the tension steel force is D minus D prime. That's what we are looking at. And the compression concrete force is 85% F sub C prime A and B. The A, B were dropped, I think, in this expression. It should be 85% F sub C prime A, B. Add those on your, and we will issue a corrected. I went over the slides meticulously yesterday. I didn't catch it. This is the lever arm of the compression concrete force. This is the compression steel force, and this is the lever arm of that force. Okay. The compression steel stress is the strain in the compression steel multiplied by the modulus of elasticity of the steel. Okay. Or if the compression steel strain goes beyond the yield strain, then the compression steel is also yielding, and then the compressive steel stress is equal to the yield strength F sub Y. It is as simple as that. Okay. So some numbers. Same 300 by 500 section. Same 3 number 25 bars here. We have added now 2 number 20 bars as compression reinforcement. The clear cover at the top is also 1.5 inch, 40 millimeters. That is the required minimum cover for a beam. F sub C prime, F sub Y as before, no change. So the only difference between this example and the previous one, we have added the 2 number 20 bars. Okay. There is nothing here that I haven't explained. The strain distribution, the stress distribution, the compression concrete force, the compression steel force, the tensile steel force, and what is not marked in the picture is the distance from the extreme compression fiber to the centroid of the compression steel is D prime. Okay, so now we are determining, remember from yesterday, the depth to the extreme tension reinforcement is D sub T. That is, we in the previous example, we simply called it D because there is one layer of reinforcement, it does not make any difference. D is the same as D sub T. D sub T as determined in the previous example, 435 millimeters. The total depth minus the clear cover minus the stirrup diameter minus 1/2 of the diameter of the longitudinal bar. D prime, the distance from the top to the centroid of the compression reinforcement, is the clear cover of 40 millimeters plus the stirrup diameter plus half the diameter of the compression bar. This is another mistake. The compression bar is 20 millimeters, so that should have been 20 by 2. So that would give us 52 plus 10, so 62 millimeters rather than 65. We will make that correction. Again, I see these things only while presenting, not before. We did say 20 millimeter bars. Okay, so that should have been 62. But that, listen, this is how it goes. So the width is 300 millimeters. So the total tension reinforcement, 3 number 25 bars, total area is 1470 square millimeters. And the total area of the compression reinforcement, 2 20 millimeter diameter bars, is 628 square millimeters. Okay, A sub S prime. Assume the tension reinforcement strain is larger than yield strain, and that the compression steel strain is less than or equal to yield strain. So tension reinforcement is yielding, compression reinforcement is not yielding. These are assumptions at this stage. Okay, equating the total compression in the concrete stress block and the compression steel. So we have two compressive forces, one in the concrete, compression concrete, one in the compression steel. The total compression we would equate to the total tension, A sub S, F sub Y. Okay, this is compression in the concrete. This is compression in the compression steel. This is tension in the tension steel. Equating, we find the stress block depth, which will give us also the neutral axis depth. Okay, so determine the depth of neutral axis. Depth of stress block is beta sub 1 times the neutral axis depth. For 40 MPa concrete, we already established beta sub 1 is 0.76. So the stress block depth is 76% of the neutral axis depth in our case. Oh, sorry, it's okay. So at nominal strength, strain in the extreme compression fiber is 003. Thus, for a linear strain distribution, epsilon sub S prime, that is the strain in the compression steel, is 003, the extreme compression fiber strain, multiplied by C minus D prime by C. This is because of straight line strain distribution. I don't want to go back to the figure again, but this is pretty straightforward. And that gives us a D prime of 65 millimeters. This is the, I'm sorry, it doesn't give us where. So the strain in the compression steel is equal to this from straight line strain distribution, where this D prime was established to be 65 millimeters. Should have been 62. We miscalculated slightly, 65 millimeters, but that's the number that we have carried through the example. Now the force equilibrium equation, compression force in the concrete, compression force in the compression reinforcement equal to tensile force in the tension reinforcement. We put all the numbers in. You notice that we write A equal to 76% of C, so that everything is in terms of C. That gives us a quadratic equation involving the neutral axis depth. When you solve the quadratic equation, there are two solutions. One of the solutions will not make any sense. The sensible solution is the neutral axis depth. It came out in our case to 73.8 millimeters. Okay, 73.8 millimeters. So the stress block depth is 76% of that. That is 56 millimeters. Now we can determine the strain in the compression reinforcement by straight line strain distribution. that comes out to 0004, and that is less than the yield strain of the compression reinforcement as we postulated. So the compression reinforcement is not yielding. That means the stress in the compression reinforcement is the yield strength multiplied by the actual strain in that reinforcement divided by the yield strain. Okay, this is again kind of a straight line interpolation. At 0021 strain, the stress would be 420 MPa. At 0004 strain, what is the stress? And the answer is 80 MPa. So in the compression reinforcement, we have a stress of 80 megapascal, although the yield strength of that reinforcement is 420 MPa. The strain in the tension reinforcement by straight line strain distribution is 0.15, that is way over the yield strain. So the tension reinforcement is yielding as we postulated. Remember, our assumption was compression reinforcement is not yielding, tension reinforcement is yielding. Both assumptions turn out to be good. So now we are in a position to calculate the nominal moment strength, and it is again nominal moment strength because the extreme compression fiber strain is 003. So we will take internal moments of the forces. So we are taking, in this case, moment about the neutral axis. That doesn't make any difference where you take your moments. So this is the tensile steel force multiplied by its distance from the neutral axis. This is the compression concrete force multiplied by the distance of this resultant force from the neutral axis, that would be C minus A by 2. Then the compressive steel force multiplied by its distance from the neutral axis, which would be C minus D prime. When we put all the numbers in, it comes out to 249 kilonewton meters. Okay, so I do want to point out, this is interesting, the tensile steel is contributing 223 out of the 249 kilonewton meter of moment strength. The compression concrete is contributing 26 out of 249. And look at this, the compression reinforcement, 0.44 kilonewton meters out of 249. This is typically the case. If you have compression reinforcement, it does not contribute typically a whole lot to moment strength. And things are a lot simpler if we simply neglect the compression reinforcement. I'm not telling you to neglect it. All I'm telling you is that many designers simply forget about that. They just disregard it, and there is no detriment that I'm aware of. Okay, you don't. It doesn't make much of a difference, but theoretically, definitely you should consider it. Okay, the strain in the tension reinforcement is 0.15, which is way over the yield strain. So it's a tension control section making phi equal to 0.9. So for a nominal strength of 249 kilonewton meters, we have a design strength of 90% of that, which is 224 kilonewton meters. Okay, so singly reinforced section, doubly reinforced section, then we go to a flange section, a T-beam as we typically refer to it. And this is important because it is very common. We have in concrete, at least in cast-in-place concrete, monolithic construction where the slab is built integrally with the beam, and a part of the slab, as shown in this picture, acts as part of the beam. Okay, so when you apply loads on this beam, the part of the slab on both sides act like flanges of that beam. Those also bend under, just as the top portions of the beam go into compression. The flange portions of the flange close to the beam also go into compression. They effectively become part of the beam. Now, how much of the slab acts together with the beam, that's where the effective flange width concept comes in. Okay, so effective flange width is the width of the slab that participates with the beam in resisting transverse loads. ACI 318 as well as BNBC gives you the effective flange width that you should use in calculations. The BNBC provisions are, for whatever reason, in Appendix J, not in the main body, if I can call it that. Okay. So when you have flanges on both sides, effective flange width of T-beam is the smallest of three things. 1/4 of the span of the T-beam. The span of the beam would be into the screen and out of the screen. Okay, that would be the span. Beam width plus 16 times slab thickness, 8 times the slab thickness on either side. So the beam width plus 16 times the slab thickness, 8 on either side. Number 3, beam width plus clear span to the next web. So on either side, so the beam width, and we go halfway to the next beam. So from here to there, to the face of the next beam, let us say we have a distance of 8 meters. So 4 meters would be the effect, will be part of the effective flange on one side. On the other side, if there is also another beam 8 meters away, we get an effective flange that is 4 meters. Okay, the 4 plus 4 add to 8, which is the clear distance to the next cross beam. So beam width plus clear span to the next web. I hope this is totally understandable. If you have a flange on one side only, an L beam rather than a T beam, then the effective width is beam width plus 1/12 of the span length. We go from 1/4 to 1/12. Beam width plus 6 times slab thickness. You remember it was 8 times slab thickness on either side. We go to 6 times. And then beam width plus 1/2 the clear distance to the next web. That this is no different from when you have flange on two sides. After determining effective flange width, find stress block depth from force equilibrium, then nominal flexural strength is computed by moment equilibrium. That part is no different. Okay, so let's best is to go to some numbers, because that I cannot get rid of it. Yeah, that's okay. So flexural strength of a T section. A floor system consists of a 75 millimeter thick concrete slab supported by continuous T-beams of 8 meter span. Okay, so the slab thickness is 75 millimeters, and the beams, the T-beams, have a span of 8 meters. The beams are 1200 millimeters on center. Okay, so center to center distance between T-beams, neighboring T-beams, is 1200 millimeters. Web dimensions are B sub W 300 millimeters, that's the width of the T-beam. Sub W is for web. Now there is a flange and a web. And H, the total depth, is 525 millimeters. This H is pretty problematic in ACI 318. You have to always figure out what it means. For a beam, H is the total depth. Tensile steel consists of 3 number 25 bars at 460 millimeters from top of slab. So the effective depth is directly given in the problem statement. Determine the design flexural strength of the T section. F sub C prime is 40 MPa, F sub Y is 420 MPa. Okay. So this is our section that we have to determine. I will show you the calculation, but what is given is 300 millimeters wide, 525 is the total depth, 460 is the effective depth, and 3 number 25 bars. Also, the slab is 75 millimeters thick. So other than the 1200 millimeters, all the information in this figure comes from the problem statement. 300 millimeters wide beam, 525 total depth, 460 is the effective depth, 75 is the slab thickness or flange thickness, and 3 number 25 bars. So what is the effective flange width? Is the smallest of 3 things. 1/4 of the span. Our span is 8 meters, so 1/4 of that is 2 meters, 2000 millimeters. The web width plus 16 times the flange thickness. Web width is 300, 16 times the flange thickness of 75 millimeters. That must have come to the 1200, and that gives us 1500 millimeters. Okay, so B sub W is 300, 16 times H sub F is 75, 16 times 75 is 1200, that gives us 1500 millimeters. And then the web width plus clear distance to next web. The web width is 300, and remember the beams are 1200 millimeters center to center. If they're 1200 millimeters center to center, then the clear distance between them is the 1200 millimeters minus the beam width, which is the 900. Okay, so that gives us 1200 millimeters. So the effective flange width is the smallest of 2000 millimeters, 1500 millimeters, 1200 millimeters. That obviously governs. And A sub S, as in previous examples, is 1470 square millimeters. Okay. So when we calculate strength of T-beams, what we do initially assume that the neutral axis is in the flange. Okay. If the neutral axis is in the flange, then the T-beam is actually a rectangular section as wide as the effective flange width, because tension concrete doesn't count. Please follow me closely. This is obviously very important. So initially we assume that the neutral axis depth is in the flange, that the neutral axis depth is no more than the flange thickness. If that is the case, the T-beam, for purposes of flexural strength calculation, is a rectangular beam as wide as the effective flange width, because the tensile, that the concrete in tension below the neutral axis doesn't count. We neglect it anyway. Okay, so this is the calculation we are about to run. So if the neutral axis depth is no more than the flange thickness, then 0.85 F sub C prime, this is the uniform compression across the stress block, times the stress block depth times the flange width, the effective flange width, is equal to the tensile steel force. Okay, so 85% F sub C prime is 40 MPa. Stress block depth is what we want to determine. B sub F is 1200 millimeters. We calculated that the effective flange width is equal to A sub S of 1470 multiplied by 420. So A comes to 15.1 millimeters. And that is less than the 75 millimeters flange thickness. So the neutral axis is in the flange as we postulated. Therefore, the T section is a rectangular section with flange with the T section is a rectangular section with width equal to the effective flange width. Then the nominal moment strength is A sub S F sub Y, the tensile steel force times the lever arm. Tensile steel force is 1470 square millimeters times 420 MPa multiplied by D is 460. This was given in the problem statement, minus the calculated value of A is 15.1 millimeters divided by 2. That comes to 279.3 kilonewton meters. It can be easily shown that section is tension controlled, which makes the design moment strength 90% of the 279.3, and that's 251.4 kilonewton meters. Okay. I have the rest of this example to go, where the stress block depth will be larger than the flange thickness. So that will force us to do T-beam analysis, as we call it. And then I have design versus analysis. It's 9:20. Yesterday, Bodhi told me there were requests for a short break. I totally understand because the sessions are long. So we will take exactly 5 minutes. It's 20 after the hour of 9. We will start at 25 after without fail. If you if you are not back, then you will miss out. Okay, so 5 minutes short break, and then we will start again at 9:25.
Dr. Ghose.
Okay, the 5 minutes are up. So we start again. It is the same T-beam, except that we have drastically increased the reinforcement from 3 number 25 bars to 10 number 32 bars. Okay, so a floor system consists of, I don't know that there is any point in reading. Everything is the same as before, but the tension reinforcement is 10 number 32 bars instead of 3 number 25 bars. And 10 number 32 obviously had to be placed in 2 layers. 1 layer would not do. So all the dimensions are the same. 525 total depth, 400 is the width, 460 is now the not the effective depth, but the depth to the extreme tension layer. D sub T is now 460, okay, as clearly shown in the picture. Now the when so I think I misspoke. I may not have, but let me clarify. So I may have said as long as the neutral axis depth is less than the flange depth, it's not neutral axis depth. As long as the stress block depth is less than or equal to the flange thickness, a T-beam is no different from a rectangular beam as wide as the effective width. However, if the stress block depth, not neutral axis depth, if the stress block depth exceeds the flange thickness, then we have to do so-called T-beam analysis, which is what we are about to do. With that much reinforcement, 10 number 32 bars, there is absolutely no question that the stress block depth will be larger than the 75 millimeters of flange thickness. Okay, remember force equilibrium. If the tension is high, the compression will need to be high, and that would mean the neutral axis will have to come down. We will need a deeper compression block. So we are certain that the stress block depth with that much tension reinforcement will be more than 75 millimeters. Now, when that happens, this is how we deal with the situation. We find a steel area that is equivalent to the overhanging flanges. You will see that calculation. The idea is the compression that is resisted by the overhanging flanges will be resisted by how should I say, A sub SF times F sub Y will be equal to the compression that is carried by the concrete in the overhanging flanges. Okay. So that is equivalent to the overhanging flanges, a steel reinforcement area equivalent to the overhanging flanges. We will consider the same area of tension reinforcement where the tension reinforcement is actually located, and that if we take those out, that will leave us with a rectangular section where there is only tension reinforcement, and the tension reinforcement area is the total tension reinforcement area minus whatever we have removed. Okay, I think this is a pretty clear concept. We replace the overhanging flanges with an equivalent reinforcing steel area, and that reinforcing steel area will have a centroid coinciding with the mid depth of the flange. That's where it is located, H sub F over 2. So that is equivalent to the overhanging flanges. We take an equal tensile reinforcement area at the bottom. That leaves us with a rectangular section, okay, this part of the section, and the reinforcement now is the total reinforcement that exists minus the reinforcement that we took out. Okay. So let's do this calculation. Our D is the 460. So D sub T is 460. The clear distance between the layers, I don't know, it must have been given somewhere, is taken as 16 millimeters. And then the so 460 is to the centroid of the extreme tension reinforcement. Okay, so we will take away half the diameter of that bar and half the distance between the clear distance between the layers. So 460 minus half the diameter of the extreme tension reinforcement, and the gap between the two layers must have been 32 millimeters. We are taking half the gap. That gives us an effective depth of 432 millimeters. It can be checked that effective flange width remains at 1200 millimeters, what we calculated in the last example. Okay. That will give us an, well, we are checking whether the stress block depth is larger than the neutral axis depth. Okay. So if the stress block depth were no larger than the flange thickness, then the stress block depth would have been, as you see here, the tension reinforcement force divided by 85% F sub C prime B sub F. And that comes out to 82.8 millimeters. That is larger than 75 millimeters. So this confirms, as we suspected, that the stress block depth is larger than the flange thickness. So we find this equivalent reinforcement area, the reinforcement area equivalent to the overhanging flanges. The overhanging flanges have uniform compressive stress of 85% of F sub C prime. The width of the overhanging flanges is the effective flange width minus the depth of the beam, the web, not depth, the width of the beam, the web width. B sub F, the flange width, the effective width minus the web width is the total width of the two overhanging flanges multiplied by the flange thickness. So this would be the total compression carried by the overhanging flanges. That divided by F sub Y, the yield strength of reinforcement, is the reinforcement area equivalent to the overhanging flanges. That comes to 4857 square millimeters. So the moment strength contributed by this and that is the area that we just computed multiplied by the D, the 432 that we just calculated, minus 1/2 of the flange thickness, which is 37.5. So that part of the nominal moment strength we are calling M sub N1. That is the A sub SF that we calculated, 4857 times the yield strength minus, as I said, D minus H sub F over 2. So 4857, 420 is F sub Y, D is 432, H sub F over 2 is 37.5, All of that gives us 804.8 kilonewton meters. This is contributed by the overhanging flanges, if you like. Okay, so the tension reinforcement left in the remaining rectangular section is the total of 8040 minus the 4857 that we took out, that is 3183 square millimeters. The total tension in that reinforcement is 3183, the area, multiplied by 420, the yield strength of the tension reinforcement. We equate that to the compression concrete force, 85% of F sub C prime, 40 MPa, multiplied by the width of the beam, 400, multiplied by the stress block depth. That gives us a stress block depth of 98 millimeters. This is the stress block depth for that section. Okay, this section. 98 millimeters. So now we can calculate the nominal moment strength contributed by that part of the section. The 3183, the total reinforcement in that part of the beam, 420 MPa is the yield strength, 432 is D minus A of 98 millimeters by 2. That comes to 512 kilonewton meters. So the two parts together, 804 and 512, is 1317 kilonewton meters. So as far as strength calculations, that those are all the cases you will encounter: singly reinforced section, doubly reinforced section, and T section, unless you go to non-rectangular sections, which are more involved, but no new principles or anything. You just have to deal with the shape. Okay. Now, analysis versus design. What's the difference? Analysis is given section, including dimensions and reinforcement and material strengths, determine strength. That's what we were doing so far. We were analyzing. What is design? Given required strength, how much is required, or information from which required strength can be obtained through analysis. So given required strength and material strengths, determine section, including dimensions and reinforcement. So that's design. Okay, now we have to talk about but I would like to talk about a couple of things, some of which was covered yesterday. Anyway, so balance strain condition. I mentioned it kind of in passing yesterday. Balance condition is when the tension reinforcement yields at precisely the same time that the compression, the extreme compression fiber strain reaches a value of 003. Okay, so the tension reinforcement area that will produce balance condition is A sub SB, B for balanced. Corresponding neutral axis depth is C sub B, and the corresponding stress block depth is beta sub 1 C sub B. I think this figure is totally self-explanatory. All we have done is the area of the reinforcement is the balanced steel area, and so the tensile steel force is the balanced area multiplied by F sub y. Maximum strain at balance strain condition. Maximum strain at the extreme compression fiber of concrete reaches 003 at the same time as the tension reinforcement at tensile strain, as I told you 10 times at least. So under that condition, if it is a balanced section, C sub B over D, the balanced neutral axis depth divided by the total depth, is 003. divided by 003 plus F sub y divided by 200,000. This is plain straight line strain distribution. Okay, we have 003 at the extreme compression fiber. We have yield strain in the tension reinforcement, and that gives us C sub B, the ability to calculate C sub B. Now, maximum reinforcement, as I mentioned yesterday, before we embraced unified design in ACI 318M, the maximum reinforcement we could put, the maximum tension reinforcement we could put in a section was 75% of the balanced reinforcement. 75% of A sub SB, and A sub SB was typically written as rho sub B times BD, B being the width, D being the effective depth. Rho is the tension reinforcement ratio. Okay, so 75% of rho balanced is the maximum we could put in. When unified design came, and that's what we are doing even now, we have replaced that requirement by saying the net tensile strain epsilon sub T cannot be any less than 004 in a flexural member, which is defined as a member with factored axial compressive load less than 10% F sub C prime A sub G. All of that we discussed yesterday. Okay. So this is a summary of things that we talked about yesterday. So the minimum epsilon sub T now is 004. Minimum epsilon sub T for tension control sections is 005. Minimum epsilon sub T that you need if you are going to redistribute bending moments is 0075, as I also mentioned yesterday. Okay, 004 is the strain below which you cannot go in a beam section. 005 gives you a tension control section. 0075 allows you to redistribute bending moments. Maximum, before unified design, maximum reinforcement ratio used to be 75% of rho balanced. And back in those days, we could not we could not take any moment redistribution unless, if the tension reinforcement exceeded half of rho balanced, we could not do any moment redistribution. Okay, so I think this is a very nice figure to correlate past practice with what we are doing now. Now, flexural members with small amounts of reinforcement. So that is the topic of maximum reinforcement. Okay. And in design, we have to consider all of these things. How much is the maximum, now minimum reinforcement? This is also a consideration in design. Flexural members with small amounts of reinforcement experience sudden failure as the concrete strain at the extreme tension fiber exceeds the modulus of rupture. To prevent this, minimum reinforcement is specified. This is extremely important. The idea is that a reinforced concrete beam must not fail like a plain concrete beam. A plain concrete beam fails all of a sudden as soon as the first crack opens up. There is nothing to arrest that crack. And we do not want that. We want failure with warning. We want failure to be preceded by cracks that we can see, by deflection that is visible. Okay, so we need a minimum amount of tension reinforcement for a reinforced concrete beam to behave like a reinforced concrete beam and not like a plain concrete beam. Okay, so there must be enough reinforcement to arrest the cracking. The cracking, as soon as it starts at the extreme tension fiber, should not go all the way through, causing the failure of the beam. It would go to the level of the tension reinforcement. It will be arrested there, then another crack will open up, another crack will open up, and so on and so forth. So this is the idea behind the minimum reinforcement. Okay. So the minimum reinforcement that we must provide in a beam is given by this expression. However, we can never go below 1.4. Again, in metric, I don't have any feel for this. So in our units is 3 square root of f sub c prime over f sub y, and this is 200 b sub w d over f sub y. Anyway, so the minimum tension reinforcement that we must provide in a beam is given in the code. Now, if it is a flange section, then the b sub w here, this is the same expression as on the previous slide. This is for a rectangular section. Now we are talking about a flange section. For a flange section, this b sub w is replaced by either 2b sub w or the width of the flange, whichever is smaller, for statically determined members with a flange in tension. Now, very importantly, that minimum need not apply if you have provided 1/3 more reinforcement than is needed, than is required by your calculations to carry the loads. Okay, so the requirements are waived when A sub s provided is equal to or greater than 4/3 of A sub s that is required. And how much reinforcement is required is obtained from analysis of the structure under the service level loads that we are trying to carry. Okay, so this is a very, very important exemption that we try to take advantage of when we don't want to provide minimum reinforcement. Okay. So we talked about maximum reinforcement. Epsilon sub t shall not be any less than 0.004. We talked about minimum reinforcement so that a reinforced concrete beam will not fail like a plain concrete beam. Now we are talking about crack control reinforcement. This is also required in ACI 318. Crack control in ACI 318 now for several editions. We made a switch, I don't remember at which edition, but anyway, before 08. We now do crack control by limiting the spacing of the extreme tension reinforcement. Okay, so spacing of reinforcement closest to the tension phase S shall not exceed the value given by this the expression that you see, 380 times 280 over F sub S. F sub S is the stress in the tension reinforcement under surface level loads, and we will talk about that, minus 2.5 times clear cover. Now this has to be less than that. So the spacing of reinforcement closest to the tension phase shall not exceed this value, which must be less than that value. Okay, and you will see numbers. C sub C is the least distance from surface of reinforcement or precessing steel. Okay, clear cover, as I said. Now spacing S, let's skip this. If there is only one reinforcing bar, then the spacing is the width of the section. That's all this is saying. Now this is important. Reinforcement stress F sub S closest to the tension face is computed based on unfactored moment. As I said, service level loads, unfactored moment is better description. It is permitted to be taken as two-thirds of F sub Y. And that's what we almost always do. We don't try to calculate F sub S. Two-thirds of F sub Y. Okay, so that's crack control. Maximum spacing of extreme tension reinforcement that's imposed by 318. Then skin reinforcement. This is for deeper beams. And you will see pictures. So longitudinal skin reinforcement should be provided as indicated below when the height of beam or joist is larger than 900 millimeters. Okay? So these are for deeper beams. Uniformly distributed on both side faces of the member over 1/2 of the effective depth from the tension face. I will show you picture. Okay, so this is a deep beam, total depth H. So if this is the tension face, the skin reinforcement will be provided as shown in the picture, up to H by 2. Okay, this is H by 2. If this is the tension face, then the skin reinforcement will be provided as in the right-hand picture. So uniformly distributed on both faces of the member over H over 2 from the tension face. Spacing is the same as this spacing. Okay, so spacing of skin reinforcement is the same as the spacing given by these expressions. Sorry. Can be included. The skin reinforcement can be included in strength computation. You are allowed to do that if the stresses of skin bars are determined by strain compatibility analysis on the basis of straight line strain distribution. But be careful, if you are going to count the skin reinforcement, it has to be properly developed. Very, very important. Okay. Now, I may forget by the time I end. My intention is next week to cover shear, development length, and columns. I have 3 sessions. This is what I plan to do. Whether I can squeeze torsion into the shear discussion, I do not know yet. Torsion to me is not that terribly important in the scheme of things. We don't deal with that all that terribly often, but I would still like to bring it in. And if today's thing seems elementary to you, it will not appear that way at all when I go to shear and development length and so forth. So it will get more complicated in a hurry. Okay, so that's kind of the plan. Okay, once we got into design, we talked about maximum reinforcement ratio, minimum reinforcement ratio, the crack control through imposing maximum spacing on the extreme tension reinforcement, and now skin reinforcement, which is for deep beams only, depth exceeding 900 millimeters. Okay, beam span. Everything has to be tied down. So span length of members not built integrally with supports shall be considered as the clear span plus the depth of the member need not exceed distance between centers of supports. I think if you read it, it's clearly understandable. In analysis of frames or analysis of continuous construction or determination of moments, span length shall be taken as the distance center to center of supports. This is what 318 and BNBC tell you directly. In analysis of frames or continuous construction, for determination of moments, span length shall be taken as the distance center to center of supports. For beams built integrally with supports, design on the basis of moments at faces of support shall be permitted. This is what we do all the time. Okay, the joints are treated as so-called rigid zones. We calculate moments at the faces of the, so beam moments are calculated at the faces of the columns, and we design on that basis. It shall be permitted to analyze solid or ribbed slabs built integrally with supports. Slabs built integrally with supports with clear spans no more than 3 meters as continuous slabs on knife edge supports with spans equal to the clear spans of the slab and width of beams otherwise neglected. You may have to read it twice, but and this is a very specific thing that I don't want to spend time on. It is totally understandable if you read it. Okay, then we go to deflection. In design, all of those things come in. Analysis is analysis, find me strength, but design involves all of these aspects. So reinforced concrete members subject to flexure shall be designed to have adequate stiffness to limit deflections or any deformations that adversely affect strength or serviceability of a structure. Okay, deflection control in ACI 318. I would like to go through this a little quicker because I'm not saying deflections are unimportant, but when it comes to calculation, we really do not have a handle on it even today. It's just a matter of fact. Calculated deflections are routinely different from actual deflections by 50% or more. Anyway, let's go through. The idea is what are the code requirements, and that obviously needs to be okay. So deflection control, first of all, one-way construction, non-pre-stressed one-way construction. The way ACI does it is if you provide the minimum thickness, then you shouldn't have deflection problems. Okay, there are no assurances, but that's kind of the implication. So if you provide a minimum thickness, you do not have to do deflection calculation or anything like that. And the minimum thicknesses are given by this table 9.5A in ACI 318.661 in BNBC 2020. Okay. In the table, you see solid one-way slabs and then beams. So these are solid one-way slabs. These are beams or ribbed one-way slabs. So pretty much everything is covered, all one-way construction. These are simply supported beams or slabs, one in continuous, both in continuous cantilevers. So pretty much everything is covered. Okay. L is the span length. In this case, it is center to center, as was said. I forget which slide. Remember, continuous construction or frame In analysis of frames or continuous construction for determination of moment, span length shall be taken as the distance center to center of supports. So that is the L that you see in ACI tables. So the primary way of deflection control is provide minimum thickness. Values given in table 95A shall be used directly for members with normal weight concrete, grade 420 reinforcement. For other conditions, the values shall be modified as follows. So if it is lightweight concrete, there is a modification to the values given in the table. I wouldn't go into the modification. If the yield strength of the reinforcement is different from 420 MPa, then there is a modification of the values. And again, the detail you will look up. So there are tabulated values. The tabulated values are for normal strength concrete, grade 420 reinforcement. If you have lightweight, when I said normal strength, normal weight, I meant. So the tabulated minimum depths are for normal weight concrete, grade 420 reinforcement. If you have lightweight concrete, there is an adjustment to the table. If you have other than grade 420 reinforcement, there is an adjustment to the table. If you have lightweight concrete and reinforcement with a yield strength other than 420 MPa, then there are two modifications, both to be applied. So this is deflection control by providing minimum depth. There is also deflection control by computation. So if you are unable or unwilling to provide the minimum depth required by ACI 318, you can go with thinner members, shallower members, provided you can do deflection computation and show that the computed deflections are within tolerable limits. This is where I'm saying there is a this is far from exact what we do. Anyway, so where deflections are to be computed, deflections that occur immediately on application of load shall be computed by usual methods or formulas for elastic deflections, considering effects of cracking and reinforcement on member stiffness. So remember from yesterday's discussion, there is immediate deflection and then there is long-term deflection due to creep, shrinkage, and so forth. So we have to calculate both parts. Immediate deflection will be calculated by elastic analysis, and that involves stiffness assumptions. Okay? And we are being told that you shall consider cracking and reinforcement. Short-term deflection occur immediately. This I'll let you read, the factors that influence short-term deflection. Okay. In calculation of short-term deflection by ACI 318, the modulus of elasticity of concrete that you use is given by this expression. This is in metric. Okay. And for normal weight concrete, E sub C, this equation may be simplified into that equation. Okay. So these are no two different equations. This is the equation. A simplified version of that equation is this. And the simplified equation may be used for normal weight concrete. So this is our mental picture stipulation, whatever. Initially, the section has gross moment of inertia. Then when it cracks, it has cracked moment of inertia. Okay. M sub CR is the cracking moment. M sub A is the service moment. Yeah, that's what it's. I said it without looking, but that's exactly what it is called. So this is moment caused by service level loads. And the slope of this line is the effective moment of inertia. Okay, so I gross, I cracked, and I effective. This is the so-called transform section. So to figure out the crack moment of inertia. So this is our section, the strain distribution, the concrete below the neutral axis is disregarded in computations. This is the reinforcement at depth D from the extreme tension fiber. And we are taking an equivalent concrete area, if you like, the reinforcement area multiplied by the modulus of elasticity of the steel divided by the modulus of elasticity of the concrete. Okay, so transformed. So this is a transformed concrete section. By so if we, as it says here, by taking moment of areas above the neutral axis, we can write this expression solving for, so that gives, we can find the neutral axis depth from this expression. And once we have the neutral axis depth, the cracked moment of inertia from strength of materials comes out to this. So we can find the cracked moment of inertia by going to the transform section concept. And once we have our gross moment of inertia, which is easy to calculate, and the cracked moment of inertia, this is the effective moment of inertia that ACI tells you to use in computation. M sub CR again is cracking moment given by this expression. The F sub R is the modulus of rupture. We saw the expression for that. And anyway, so this is the effective moment of inertia that you are supposed to use in deflection computations. For continuous members, there are positive moment sections, negative moment sections. I sub E shall be permitted to be taken as the average of values for the critical positive and negative moment sections. This is kind of important. Okay, we are not dealing with one section. We are not calculating section deflection. We are calculating member deflection. Okay, but everything we have done is for a particular section. So what is the member moment of inertia or stiffness? And so so this is saying that you take average moment of inertia of the negative beam sections and the positive beam sections and use that for the entire beam. Long-term deflection. So the short-term deflection can be calculated. Long-term deflection, how do we do it? To cut a long story short, I will let you read the slides, what influences what. So long-term deflection, we have a very crude approach to it in ACI 318. We simply multiply the short-term deflection by a lambda sub delta, and that lambda sub delta times the immediate deflection is the time-dependent deflection, the increase in short-term deflection. Okay, so I will repeat. There is short-term deflection. There is time-dependent increase in the short-term deflection, and the two together, the immediate deflection and the increase due to creep and other factors, give us the total deflection. The time-dependent increase is estimated by applying this multiplier to the short-term deflection. The multiplier is a function of the compression reinforcement ratio, because it is an established fact that if you have more compression reinforcement, that helps in relieving the effects of creep, and that decreases long-term deflections. This is why this is in the denominator. Okay, and this psi is a time-dependent factor. So if we are interested in deflections 5 years or more from the time of loading, the psi is equal to 2. Okay, so if you don't have any compression reinforcement in your beam, and you want the time-dependent increase in deflection, let me let me make sure that I said one thing right. So lambda sub delta, I said it wrong. Now I realize. Okay, so lambda sub delta gives you the total deflection at the end of so many years. This will be so we are saying that after 5 years, the total deflection will be twice the immediate deflection. So the long-term increase will be 1 times the short-term deflection. That's what this multiplier is. Now, these two, large as it seems, most knowledgeable people think it's totally inadequate, that the actual deflections after 5 years would be much more than twice the immediate deflections. But this is what ACI 318 tells you, and this is what you go with. Okay, so short-term deflection at the end of whatever period of time. Now, what are the deflection limits? So now you come to table 9.5b. Okay, so there are 2 parts to the table: flat roofs not supporting or attached to non-structural elements likely to be damaged by large deflections, and then supporting or attached to non-structural elements likely to be damaged by large deflections. If they are likely to be damaged, we have tighter limits, L over 360. If they are not likely to be damaged, roofs not supporting or attached to non-structural elements likely to be damaged, then it is L over 180. Okay, so the limits, those limits, very, very importantly, apply to immediate deflection due to live load. Okay, so that is the first set of limits that we deal with: immediate deflection due to live loads alone. Those are the limits. The next set of limits apply to, again, non-structural elements likely to be damaged and non-structural elements not likely to be damaged. Likely to be damaged, the limit is tighter, deflection limit. Not likely to be damaged, we have more liberal limit. Okay. Now, what deflection do the limits apply to? That part of the total deflection occurring after attachment of non-structural elements, which means some of the long-term deflection due to all sustained loads. So long-term deflection due to all sustained loads, and the immediate deflection due to any additional live load. Okay, so please try to understand this. So that part of the total deflection occurring after attachment of non-structural elements. So as soon as you attach the non-structural elements, there will be immediate deflection due to the additional loads. And so you take that plus the long-term deflection due to all sustained loads. Sustained loads will be dead loads, could be superimposed dead loads, so some of the superimposed live load, whatever is sustained, the long-term deflection due to that. There are those notes and so forth, which I think it is already maybe too detailed, so I will let you read. Those are all important things, but I will not go into that. It's kind of on the long side already. I want to leave time for questions. Anyway, so moment redistribution. This we went over yesterday, so this is a repeat. I'll do that very, very quickly. Moment redistribution today, you can decrease the negative moment, in which case the positive moments in the spans will increase, or you can decrease the positive moment, in which case the negative moment will increase. Okay, both ways are allowed. As indicated yesterday, permitted redistribution is 1000 times epsilon sub t. Moment redistribution starts at an epsilon sub t of 0075. Below that, you cannot take any moment redistribution. So we start at 7.5% moment redistribution. The maximum we can take is 20%. This is now irrespective of whether you are dealing with reinforced or pre-stressed concrete beams. Okay, a short example. So design a simply supported beam of span 7 meters to carry service load moments of, so M sub D is 100 kilonewton meters, M sub L is 40 kilonewton meters. Simply supported beam, 7 meter span, M sub D 100 kilonewton meters, M sub L 40 kilonewton meters, F sub C prime 40 MPa, F sub Y 420 MPa. M sub U, two possibilities. We have dead loads and live loads. So 1.4 times the dead load moment, that gives us 140 kilonewton meters, or 1.2 M sub D, 1.6 M sub L, that gives us 184 kilonewton meters. 184 obviously governs. That is the required moment strength. Beam span is given as 7 meters. Minimum beam depth is the 7 meters divided by 16. If you go back to the table that I showed you for simply supported beams, which is what this is, the minimum depth required is 1/16 of the span. That gives us 437.5 millimeters. We are going to provide 450, 437.5 or more. We are going to provide 450. The width is entirely up to us. We have said 300, that's two-thirds of the 450. And that we do something like that. Yeah, there is no hard and fast rule. Calculate approximate amount of reinforcement. So assume number 25 bars, number 12 stirrups, 40 millimeter clear cover, approximate moment arm. This is now approximate for estimate purposes only. We will make it exact in just a little bit. We are saying assume a moment arm 90% of the effective depth and assume a P factor of 0.9, or assume tension controlled sections. Okay, so this is the picture of what we are dealing with. The beam, the stress distribution to the right. The effective depth is the total depth of 450 millimeters that was given in the problem statement, minus clear cover of 40 millimeters minus stirrup diameter 12 millimeters and half the bar diameter 25 millimeters. That's 385 millimeters. So approximate moment arm is 90% of D. That's what we just said. We will assume that it is, and that will give us a lever arm, moment arm of 346.5 millimeters. Then the required reinforcement area is going to be the M sub U of 184 kilonewton meters divided by phi of 0.9, F sub Y of 420 MPa, moment arm of 346.5 millimeters. That gives us 1405 square millimeter. So if the lever arm is 90% of effective depth, then we need 1405 square millimeters of reinforcement. If we provide 3 number 25, that gives us 1470. So that's what we are going to try. 3 number 25. Now we are going to be exact. So D is 346.5. There was no, that number was pretty exact. B is 300 millimeters. Our A sub S is 1470 square millimeters. Assuming that the tension reinforcement is going to yield at nominal strength, equating total compression in the concrete to, we have done so many times, so total compression is equal to total tension. That gives us the stress block depth comes out to 60.5 millimeters. Depth of neutral axis is the 60 millimeters divided by beta sub 1. Beta sub 1 we have calculated many times for 40 MPa concrete, 0.76. So C, neutral axis depth, is 79.6 millimeters. At nominal strength, strain in extreme compression fiber is 003. So that enables us to calculate the strain in the tension reinforcement. That comes out to 0.12. That is way higher than the yield strain. So the tension reinforcement is yielding as we assumed. So now we can calculate the moment strength exactly. A sub S 1470 square millimeters, F sub Y 420 MPa, D of 385 minus A of 60.5 millimeters divided by 2, that is 219 kilonewton meters. Okay, now, well, we are still continuing. So epsilon sub S we have found is 0.12, which is larger than 0.05. So we have a tension control section. So phi is 0.9. The nominal moment strength was 219 kilonewton meters. We are establishing that the phi is 0.9. So the design moment strength is 184 kilonewton meters, 0.9 times 219. Okay. Maximum reinforcement. Remember, now maximum reinforcement is stated like the net tensile strain shall not be any less than 0.04. Our net tensile strain was calculated as 0.12, which being larger than 0.04, we have not gone beyond the maximum reinforcement prescribed in ACI 318. Minimum reinforcement given by this expression, except that we cannot go below that. This expression gives us 435 square millimeters, the other one 385 square millimeters. That obviously governs. I'm sorry, the larger number governs. We cannot go below 435 square millimeters. We have provided 1470, so we are well above the minimum reinforcement that is required for our beam to behave as a reinforced concrete beam rather than a plain concrete beam. Okay, now the crack control, the spacing of reinforcement. Assuming 40 millimeter side covers, clear spacing between bars that we have provided. We have 300 millimeter wide section. We have two clear covers of 40 millimeters, and we have three bars that are 25 millimeter diameter. So we have a clear spacing of 72.5 millimeters. That has to be, I didn't talk about these, but these are ACI requirements. The clear spacing has to be larger than the bar diameter, also larger than 1 inch. And both requirements are met. Then remember the maximum spacing of the extreme tension reinforcement. The maximum spacing is 248.75 millimeter, except that it has to be less than 300 millimeters. So this is our governing maximum spacing. Our spacing, as we just established, so this is still part of this calculation. In calculating this number and that number, we have used an F sub S equal to 2/3 of F sub Y, which is 280 MPa. And the C sub C that is required here, clear cover, is the 40 millimeters of, not clear cover. This is covered to the reinforcement, the center of the reinforcement. So 40 millimeters of clear cover plus half the bar diameter, that is C sub C. Okay. So we have provided a spacing of 72.5 millimeters. That is way below the maximum that we are determining. So we are quite okay with the spacing of reinforcement. Now I have a one-way slab, and I am thinking that time is out, and this is easy material. I think all I need to point out is that a one-way, okay, let me say a couple of things. So if you have a beam supported slab, beams on four sides, this slab will bend in both directions, in the short direction and the long direction. A larger part of the load will be transmitted by bending in the short direction because that's the stiffer direction. A smaller amount of load will be transmitted by bending in the long direction. Okay. When I say transmitted, the loads would be taken from the slabs to the beams. Now, when the long dimension to short dimension ratio exceeds 2, the long direction bending becomes almost irrelevant. Very little load is transmitted by bending in the long direction. Almost all the load is transmitted by bending in the short direction. And then we treat this slab supported on all four sides as a one-way slab, a slab like this. Okay? And a one-way slab is like a series of beams supported on the actual supports. These beams, one is exactly the same as the other. We design this beam as we have designed the beams up until now. In US practice, we will take it 1 foot wide. You will take it 1 meter wide, does not make any difference. And whatever reinforcement you calculate for that 1 meter will be So we will calculate the spacing and we will provide that reinforcement spacing throughout the slab. So that's what is kind of illustrated here. The additional thing is shrinkage reinforcement. Shrinkage reinforcement is 0.18% minimum, except that if you use reinforcement having yield strength larger than 420 MPa, then you can go below 0.18%. So shrinkage reinforcement is 0.18%, except for higher strength reinforcement, you can go below 0.18% as given by this expression. I do not know that I need to point anything else out. Yeah, the final thing is this. So for structural slabs and footings of uniform thickness, the minimum reinforcement in the direction of span shall be the same as the shrinkage reinforcement. You cannot go below 0.18%. Maximum spacing of this reinforcement shall not exceed 3 times the thickness nor 450 millimeters. Okay, so I trust that if you go through the one-way slab section, you will find it totally easy to understand, and I ran numbers, so that will make it even easier to follow. And I'm sorry, time didn't permit going over. I didn't. Maybe I took it too small. Whatever. As I said, this material I have not taught. The slides are prepared for you. I don't have a great sense of time, but I think I think I did cover 95% of what I intended to cover, and we'll have to be happy with that. Okay, I'm open to question, and we will do it the same way as yesterday. Bobby will try to read me, and I will. I'll try to answer if I can, and maybe Dr. Rakib is still here, and he can help me if I get stuck.
Dr. Akib didn't join today.
Oh, okay, okay,
Yeah,
that's it.
I have been looking for him, but he didn't join today. So, okay. So I will start with the first question. Can we assume that the concrete is made of brick chips as lightweight concrete? Sorry, can we assume the concrete made of brick chips is lightweight concrete? That's what.
It definitely is lightweight concrete, but the concrete made with brick chips are, I don't know, you have to be careful, and I don't have a lot of feel because it is not used in this country. So this is where Dr. Rakib might have had some feel, I do not know. It definitely is lightweight concrete, but it is not, how should I say? It does not enjoy all the privileges of lightweight concrete. That's not the right way to say it. There are more restrictions, and one of them came up yesterday. For something or the other, it was prohibited. Remember, so yeah, it is. Yes, it is lightweight concrete, but it is in some ways probably worse than the lightweight concrete that is used for structural purposes.
Okay. As we prefer under-reinforced beam design, but after construction of a beam, we found out by test that the strength of concrete is not up to the desired design strength. And we make beam over-reinforced. So what should we do in this case?
This is a good and interesting question. So I I am kind of surprised. So you designed an under reinforced beam, so it must have been kind of borderline because so concrete strength. So let us say you targeted concrete strength of 4,000 psi and it didn't come up to 4,000 psi. It was 3,700. So let me try to understand. That made the beam over reinforced. You are going by the old rule of 3/4 of row balanced, and the row balance changed. I'm just trying to understand. Yeah. Anyway, I'll try to figure it out for myself. But if that's what happened, because concrete strength didn't the target strength was not realized, and that made the beam over reinforced. There is nothing that you can do or are supposed to do. You will just have to live with the situation. This will be borderline over reinforced. Nothing drastic will happen. And so there is nothing to be done, but I don't fully understand. I'll have to figure that out, not sitting here trying to answer the question. This intrigues me. Yeah, but the answer is the is the answer I will stick to. There is nothing you can do, and there is nothing you need to do. It's kind of a borderline situation. The only thing I would say is you shouldn't have gone that far. that the concrete strength switches you from under reinforced to over reinforced.
Yeah.
I think you're talking in old terms, 3/4 of row balanced. Your under reinforced is up to 3/4 of row balanced, and you went just a little bit beyond. I think that's what you are saying. Okay, go ahead.
Yeah, if a beam is on one side, beam one side, column and the other side is. Yeah, I'm just trying to rephrase the question. So, if on one side of a beam there is a column and on the other side there is a shear wall, what should be the span? So the beam is bearing on shear wall.
That's fine. If the beam is bearing on a shear wall, is no different from a beam bearing on a column. I don't know. Because the shear wall is stiff, you think the span should be changed?
Yeah.
Without context, it's very difficult to. Anyway, we do computer analysis. You will put everything into the computer, and the bending moments and things will be calculated at the face of the support anyway, whether it's the beam support or column support. So I do not know why you will have to be hung up on the span. You agree with me, Bodhi?
Right. I don't think there's any difference if you have two columns on both ends or shear walls on both ends.
Yeah, and I don't know. I mean, there was a question yesterday also whether this should be designed using the overstrength factor in seismic applications, and I'm not understanding why you think that these are particularly vulnerable or whatever. There is no. So one support is stiffer than the other, but if you do proper analysis, that the effect of that will be reflected in the results. You don't have to do anything extra.
Okay. There are a lot of questions right now coming. So in section 6.3.2.10.4.1 of BNBC 2020, there is a coefficient for flat plate. Second. And that coefficient is 0.25 of IZ. What would be this coefficient for beam slab? It's very specific.
No, read that one more time.
Section 6.3.2.4.1 of BNBC 2020, there is coefficient for flat plate slab, that is 0.25 IZ. What should be this coefficient?
0.25 IG.
Yeah.
Mhm.
What should be this coefficient for beam slab?
Without looking, I do.
Yeah, I will just mark this question up, Dr. Ghosh. I think we
No,
can look at it and then.
no, it's what I'm trying to say is, so I told you next week will be shear, development, length, and column. Following week, I will do flat plate, first flexure, then shear. Now, the 0.25 I sub g suggests to me that you are talking about some kind of stiffness for flat plates. Without looking, I do not know what the context is. So when I prepared the material for the two-way slab design, I will look into it and keep your question in mind and see what it is that you are asking. So we have to do a little bit of looking. The question on the and I am not in a position to look up section such and such of BNBC. It will be pretty tough. The BNBC organization is such that I find it difficult to find things in there. So, okay. Yeah, but keep it kind of in a place where we don't forget about it. Yeah.
Some of the questions are very basic. I think most of the questions, the question answer box that I'm seeing right now,
Mm.
that has been answered in the presentation, like while you were doing.
Mhm.
So they are just asking again. For those questions, I would just request you guys that I will upload a recording afterwards. So just go through the recording. Dr. Ghosh has like gone over these things in his presentation. Okay, let me just check. Okay. So if required, compression steel in a beam
Mhm.
is found high, and if A is less than A, that small a is less than slab thickness, can we distribute rebars in part of adjacent slab to avoid congestion?
Read this one more time, please.
If required compression steel in a
Mm.
beam is
Mm.
found high,
Mhm.
and if A, that small a,
Mm.
is less than slab thickness,
Mhm.
can we distribute rebars in part of adjacent slab to
Yes,
avoid
yes,
congestion?
absolutely. Yes. Yes, and I believe there is at least later editions of ACI 318, there is some guidance on that, how far you can go. You can go into the slab, obviously. You should stay close to the beam. And there are there is some guidance limitation, but the answer is definite yes. Yes, you go into the flange. That's the right thing to do. You not only can, but that's what you should do.
Okay. And code does not prescribe any maximum strain in tension for tension control beams. Is there any best practice to follow?
Maximum. So what he's saying is epsilon sub t
Epsilon sub t, yeah.
005 onwards, it's all tension control. Is there an upper limit on?
Is there any good practice to follow? That's what he's saying that.
Let me think for a second. Haven't we taken care of that by providing minimum reinforcement ratio? Because if the tension is high, the concern, I think, will be rupture of the tension reinforcement. And we have, by providing the minimum amount of tension reinforcement, we have, I believe, taken care of that. This should be my answer. Think about it, whether what I'm saying makes sense. And so there is an effective upper limit imposed by the minimum reinforcement ratio that we have to provide, would be my answer.
Yeah, I'm just going through the questions in room 2 right now.
Mm-hmm.
Hmm. If we use 3000 psi concrete with 72.5 grade deformed bar, is it allowed? Are you aware of anything like that, BNBC?
Say that again. What's the question?
Is 3000 psi concrete allowed with 72.5 grade deformed bar?
Yes, it is allowed to the best of my knowledge, but I will tell you, low strength concrete and high strength reinforcement, you are not getting full value. Like, how do I want to put it? High strength reinforcement requires high strength concrete if you are going to get full value out of the high strength reinforcement. With low strength concrete, you will not be utilizing the high strength of the high strength reinforcement. The stresses that you will be imposing on the reinforcement will be significantly lower than the stresses that reinforcement can resist. So it is allowed, but it is inefficient.
Okay. Okay. So when the beam's capacity was checked, it was found that it was overstressed against lateral and vertical load combinations, implying that additional reinforcement in the negative section near the support is required to comply with the code. In that case, can we consider slab reinforcement up to 4 times the thickness of the slab?
Some of the time I do not quite understand the thinking. If you have a slab integral with your beam, the slab is part of the beam. And the fact that the slab is part of the beam does not depend on whether you have some perceived deficiency or not. So I do not know. Read the question again.
So when the beam's capacity was checked, it was found that it was overstressed against lateral and vertical load combinations.
Yeah. So my question is, when you say beam's capacity was checked, why didn't you include the slab in the first place? That's part of the beam. Why would you even check without the slab, without the overhanging flanges? I do not quite understand what the thinking is. So the slab in monolithic construction, part of the slab acts together with the beam. So your beam is the physical beam plus the overhanging flanges on the two sides. And this is not conditional. Okay. And if you have that beam, why would you check anything without the flanges? I don't quite understand. So that I hope what I'm saying is clear to you, and that would be your answer.
Okay.
Am I making sense?
Yeah. The question itself wasn't that clear actually. I started reading the question and then it wasn't clear to me also. So when we calculate long-term deflection of beam element, is it needed to consider crack moment of inertia, or should we use gross moment of inertia? Gross moment of inertia.
Read that one more time.
When we calculate long-term deflection of a beam element,
Mm.
do we need to consider cracked moment of inertia or gross moment of inertia?
Okay. So first of all, long-term deflection you cannot calculate. You probably can, but that's a research project. So long-term deflection we estimate by multiplying the short-term deflection by a multiplier that I talked about. And the calculation of short-term deflection or immediate deflection, ACI 318 specifically says has to be based on cracked section. Okay, so remember the I sub G, then I sub CR, and then I effective. So I effective is what you have to use in deflection calculation. It is, so you consider cracked section. That does not mean you use cracked moment of inertia, which is a fraction of the gross moment of inertia. You use the effective moment of inertia. I had a picture, remember? I don't know what going. Let me try to go back. There. Okay. So this is gross moment of inertia. This is cracked moment of inertia, much lower. You are supposed to use this effective moment of inertia as given by this expression in your immediate deflection calculation. And then long-term deflection will be a multiplier of that deflection.
Yeah. So there is one question, is long-term deflection automatically computed in the result of FEA model? That you have to see which software you are using. And
Right.
most of the software, they will do basically the same thing that Dr. Ghosh said. They will estimate it. It's not calculated. You cannot calculate a long-term deflection just like that. So that will be estimated based on like different formulas, and you have to see if the software does it automatically. Most of the software, they don't do it automatically. You have to check a button or something called to calculate long-term deflection. So be sure about that. And what is the limitation of long-term and creep deflection? I
What
think
is-
Dr. Ghosh went over it. What is the limitation of long-term and creep deflection?
The limitations are in 9.5 table 9.5b. I went over that table, and so please look at the table carefully. There are limits, but then there are deflections on which the limits apply, and that part. Let me see if I find it easily.
Yeah, as I said, like most of the questions you have already answered, Dr.
Yeah, but
The
obviously
presentation.
didn't register that part. So these are the limits, and the limits apply to that part of the total deflection occurring after attachment of non-structural components, which would be sum of the long-term deflection due to all sustained loads and the immediate deflection due to any additional live load. Okay, so after the non-structural elements are attached, if there is any additional live load imposed, immediate deflection due to that, plus the long-term deflection due to all sustained loads. That's what these limits apply to.
Yeah. What will be the allowable crack width?
What would be what?
Allowable crack width.
Allowable crack width ACI does not go into. No, we give you the maximum spacing of extreme tension reinforcement. Yeah, there used to be things said about the allowable crack width, but then we discontinued. ACI 318 does not go into that.
Just going through the questions, Dr. Ghosh.
Hmm.
A lot of the questions are related to ETABS.
Hmm.
I can answer them
Hmm.
directly over the chat.
Hmm.
Okay, and for concealed electrical piping in between slab as
Hmm.
well as beam, is
Hmm.
there any guideline that exists?
Not that I know of. Let me think. No, not really. Nothing I can cite. No,
Okay.
unfortunately. Yeah.
When we consider singly reinforced, design moment capacity is 225 kilonewton meters. At the same section, when we consider doubly reinforced, it
Hmm.
comes to 224. So can you explain why is it reducing?
Is that what happened?
Yeah, that happened according to the question. How is the strength reducing?
That is a good
And
question. I didn't. that
maybe they can share the section details. I don't know.
no, I'll find it.
That happened in the presentation. Oh,
That's what I assume is what is being asked. I don't know.
again, questions related to ETAB, stat, MIDAS, and everything. Like this session is more on the
Yeah.
conceptual of it, like side of it. Yeah, like all the software questions, like these are well answered over the over online. Even if you search, you'll find them.
So the singly reinforced section had 250. The section with 249. He's absolutely right. Okay. That is a good question. I didn't.
Yeah, maybe you have to check the numbers.
Yeah, let us not take time. I think that's an excellent question. I didn't even notice. We'll see and come up with we need to come up with an answer.
Right. That's a very, very good catch.
Yeah. Yeah. Yeah.
So is the limit software we have done. This is done.
Although I would add that compression reinforcement doesn't add anything. The contribution was minimal. I forgot now.
Yeah, it was minimal, 0.44 or something.
So the numbers are probably equal subject to rounding, and that's probably what we are seeing. Anyway, still, it's a good question, and I will, yeah. When you say decrease, it probably didn't decrease, it probably remained the same, is what I'm trying to say, because the compression reinforcement doesn't do anything. which I mentioned specifically. But let's still go over the numbers. Yeah, I think this is a round of kind of a thing that has done it. Yeah.
What is the minimum thickness of a flat plate slab?
Minimum thickness of flat plate is given in the two-way slab chapter. We will come to that week after next.
Okay. Should we consider tiles or any other material for floor finish having no partition wall as non-structural elements for deflection control?
Say that again. Shall we consider what?
Tiles
Huh?
or any other tiles?
Shall we consider tiles?
Yeah. Or any other material for floor finish
Yeah.
as non-structural elements for deflection control?
I do not understand the question. So you have tiles on your floor. What has it got to do with deflection control?
I think he's asking that should we consider the weight of the tiles and floor finish, other
The
floor finishes?
weight of the tile will cause deflection.
Yeah, so it should be.
But why? What difference does it make that we consider it non-structural or structural? I don't know. Of course, it is non-structural. So
Yeah, it is non. They are non-structural elements, and that their weight has to be considered. I don't know. Like, question is incomplete, or maybe we didn't get what exactly the person wants to ask.
What he has in mind, yeah.
Yeah. For deflection check, there is a load combination which is dead load plus 0.5 times of live load plus 0.7 times of wind load. Is there any combination to check drift? And what should be done for drift?
Where is this? Where is this combination?
Did you show that? I don't think you showed it today.
No. I didn't show it because I don't know. There may be something, I don't know the context of the question. So is there any way of corresponding with questioner?
Yeah, I'm corresponding with them.
Okay, so.
Yeah, most of the questions are there, but we are not getting the context of it.
Yeah, right. They have something in mind that doesn't always come across. It makes it difficult for us to answer.
What is the minimum size of rebar to be used in a slab?
Minimum size of rebar to be used in a slab is our number 4, which is 12 millimeters. Below that, it's even that is quite thin, but that can be used.
And yeah. Again, like most of the questions, Dr. Ghosh already answered. So I will upload the recording later. Like, it's our day right now, so I will upload the recording by our night. So you will probably see, you all will see the recording by tomorrow morning. So please go through the recording. Most of the questions that have been asked are already answered during the presentation. And Dr. Ghosh, it's already 11:05 now.
Yeah.
We have crossed the time.
Yeah.
So I think.
Okay.
Yeah. So I am saving the question and answers and the questions. So Dr. Ghosh, if you want, I can share the questions later and maybe we can come up with answers.
Yeah, we'll sort out a couple of things, the 249 versus 250. And
Right.
and I wrote down one or two other things I have to, and then we will do a posting or something.
Right.
Yeah.
Yeah. So once again, thanks for joining today's webinar. I hope you guys didn't face any problems in joining today, because we had 2 rooms.
How
And,
many today?
I think it went close to 1200 total
My goodness.
in between.
Hmm.
Yeah. So, and then it kept on, like, it was on an average there were 1150 participants.
Okay.
Yeah.
Okay.
Okay. So I will open up the quiz now, and please,
Yeah.
you have 24 hours to give the quiz. So see you in the next webinar. Next webinar will be a steel webinar, right? By Dr. Amanat, I guess.
I think Saturday, Sunday is Dr. Amanat. That's not.
Saturday and Sunday.
Yeah.
Yeah. Okay, Dr. Ghosh, thank you so much.
Thank you.
We'll end the meeting now.
Thanks, everybody. Yeah. Bye.